Hi everyone, I'm Professor McBain and welcome back to Chem 100 and welcome to our new lecture series on energy. So in this first video we're just going to define a lot of topics and we're going to start diving into the mathematics behind energy and energy transfer. Hi everyone, welcome to our next lecture video. Okay, so we've been talking about energy for a week now. We've learned mostly that energy can be transferred as heat to warm things up, right? That's what we talked about mostly in our lecture on global warming, right? So we can see that energy can definitely warm things up even if that energy is literally just IR light. We're going to learn that energy has the capacity to cause phase changes as well. This note up here at the top about energy having the capacity to do work, it's a very physics way of thinking about things. We're not going to worry too much about work versus other things. If we're utilizing energy to get anything done, we're primarily going to be looking at energy as heat that gets transferred between things, more or less. Okay, so let's start thinking about energy that can get transferred to things to warm things up by a certain amount. That's what we're going to focus on first. So let's consider, a stovetop. I've got one of those electric ranges. Okay. Let's say that we set both of those stovetops to a setting of 6 on the dial, right? Let's say that both of these stovetops also have one pot on them, and this pot is supposed to be exactly the same as the other pot in terms of what it's made of and how thick it is. But let's say that one of these pots is filled with oil and the other pot is filled with water. Let's also say that both of these pots contain 10 grams of each of their components. And so my question for you is, which one gets hot first? Well, if you've done any cooking, you should know from experience that the pot with the oil in it is the one that you really got to stick around and watch, because this one is going to get hot first. Whereas water takes quite a while to reach the same temperature that the oil reaches very quickly. Okay. So that's kind of interesting, right? If all of these conditions are otherwise the same, there is this interesting difference in how quickly different substances will heat up, even if they are receiving the same amount of energy and there's the same amount of that substance present. Okay, so this relationship between the amount of energy that a substance absorbs and how much of that energy is there and how quickly it gets hot, all three of those factors combined come together in a relationship called the specific heat. The specific heat is defined as the amount of energy required to raise 1 gram of a substance 1 degrees Celsius in temperature. It has units of joules per gram per degree Celsius. Okay, so these units, don't be too afraid with them, all right? So there's kind of like joules per gram, and then there's joules per degree Celsius. And then if you combine them with each other and you want to compare all three variables to each other, then you get this ratiometric variable that just happens to have two variables in the denominator, okay? So for example, water is going to be a substance that we talk about a lot moving forward. The specific heat of water, which by the way, the specific heat of anything is denoted with the lowercase letter c. Okay. So if I use specific heat as a variable in an equation, which I'm going to, then I'm going to denote it as lowercase c. Okay. So the specific heat of water is equal to 4.184 joules per gram times degree Celsius. So again, what that means is that if I have 1 gram of water, then I need to supply it with 4.184 joules of energy in order to raise the temperature of that water by 1 degree Celsius. So you may be wondering what a joule is in general. The joule is a very, very small unit of energy. 4.184 joules is also equal to 1 calorie, and this is a lowercase calorie. But this is meant to be a similar calorie to the ones that you find on nutrition labels. However, it takes 1,000 of these little calories in order for you to have 1 kilocalorie, which is equal to 1 capital C calorie. This capital C calorie, this is the one that you find on nutrition labels, right? So if you consume something and you just consumed like a 1 calorie bite of something, then you actually consumed 1,000 lowercase calories, or in other words, you consumed 4,184 joules in that small bite. Oh, hey, okay, wait, so if 4.184 joules is equal to 1 lowercase calorie, then that means that I can also express the specific heat of water in units of lowercase calories, and this would just be 1.0 forever, but then we could express this as lowercase calories per gram times degree Celsius. These are the same number, just expressed in different units. Okay, so let's move forward in these slides and get an idea of what that ends up meaning. So, of course, here on this slide, we get an understanding that, well, if I have 1 milliliter of water at 20 degrees Celsius, then I have to put in 4.184 joules in order to heat up that 1 milliliter sample of water by 1 degree Celsius. Oh, you notice that I switched out of grams and I am now talking about milliliters. That's not appropriate. Grams is not milliliters. That's not okay. But it actually is okay. Sorry. The density of water is roughly equal to 1 gram per milliliter. Okay, so that's why all of these notes in the book still hold true, because I'm not really talking about 1 milliliter, even though I am. This is also equal to 1 gram of water. This only holds true with water. Other things do not have densities of 1 gram per 1 milliliter. Okay, so this only works with water. Anyhow, all right, so again, we're talking about water here. If I've got 100 grams of water and I want to raise the temperature of that water by 1 degree Celsius, well, now I have to put in 100 times as much energy, and so I have to put in 418.4 joules, okay? And then if I want to heat up those same 100 grams of water by 10 degrees Celsius, then I need to calculate this. I need to multiply this energy by another factor of 10, because now I want to increase the temperature by 10 degrees instead of by 1 degree. So therefore, I've got to put in 4,184 joules of energy. So there is a slightly more methodical approach that we can use to understanding specific heats, okay, and to finding out how much energy we need to put in, or, you know, given all of these changes that we want to do to a certain mass and all of that, and so on and so forth. Okay, so we can express this all with an equation. Isn't that fun? So I can say that that gets represented as the letter lowercase q. The mass of a substance that I have present, we're going to call that lowercase m. The specific heat, just like we saw earlier, I'm going to express that as a lowercase c. And then notice that all of this has been expressed in terms of a change in temperature, right? So I can express that change, any change really, as the Greek letter delta, and then the temperature gets expressed as an uppercase T. Okay, so that's all well and good, but what I'm trying to get us to here is this expression that Q equals M times C times delta T. Delta specifically is always the, so let's see, if I was talking about delta X, for example, I would always be taking the final value that's reached and I subtract from it the initial value that we started with. So then similarly for delta T is always going to be equal to the final temperature that we reach minus the initial temperature. So I never get to reverse them, okay? So then you can imagine that if something is cooling down and your final temperature is less than your initial temperature, then that would lead to delta T having a negative sign. Yes, very good. There's my Blue's Clues moment there for you today. You're going to get to see examples of how to use Q equals MC delta T at our lecture session on Monday. And then there will be practice problems for you to work through on the homework. Remember to also check out the reading on this unit for additional worked through examples so that you have all the tools in your toolbox to apply this equation successfully. Our next topic will address the math concerned when the substance reaches its melting or boiling temperature and then goes through a phase change. You're going to see that we have to treat it differently. So I'll see you at that next lecture video.